Hello, and welcome to this presentation, An Introduction to Direction Finding. This presentation covers the basic principles of radio direction finding and provides a technical overview of the most common radio direction finding methodologies. Let's start by providing a general definition of direction finding. In this presentation, we're going to use the term direction finding to refer to the use of specialized instruments, antennas, and methodologies to determine the physical location of a source of radio frequency energy. In other words, how do we determine where a signal is coming from? As we'll see in this webinar, there are many different ways of performing direction finding, all with their respective strengths and weaknesses. One of the key differentiators in direction finding is the accuracy of the results, or how close can we narrow down the source of a signal. Clearly, we'd like as precise a location as possible. That said, accuracy requirements vary. Under some circumstances, an error of several hundred meters is acceptable, such as finding a ship in distress on the open sea. In other circumstances, we may need accuracy down to tens of meters or even single-digit meters. Accuracy is important because in many cases direction-finding targets are non-cooperative. Not only do they not want to be found, but they may take steps to hide their location or otherwise complicate the direction-finding process. Before we get into the technical details of the different direction-finding methodologies, let's spend a moment to define some additional terms that are often a source of confusion or even contention. Namely, the difference between power of arrival and angle of arrival. There are various competing definitions for these terms, but we're going to use the expression power of arrival to mean measuring the level at a given location. That is, we simply drive around and record the received RF level at the frequency of interest. Often this information is used to create a heat map, where power is plotted as a function of location. Although this methodology can of course be used to find the location of radio frequency sources, it's not really direction finding in the strict sense of the word, because we're not finding the direction towards the source. On the other hand, we can define angle of arrival as any methodology that determines the angle, that is the bearing or azimuth, towards the source. This is true direction finding in that we calculate the direction from which the signal is arriving. As we'll see in this presentation, the vast majority of direction finding methodologies are based on angle of arrival because this approach is faster, more efficient, and much more accurate than approaches based on power of arrival. So how do we determine the direction from which a signal is arriving, that is, the angle of arrival? As you know, there are three things that can change as a signal moves through space: its amplitude, its frequency, and/or its phase. So direction-finding methodologies calculate bearings using location-based variations in the received signal. Most direction-finding methodologies use a single one of these variations, that is, changes in amplitude, frequency, or phase/time to compute bearings. Bearings, which represent the direction towards a source, can be used in two main ways. A single bearing provides a direction but no distance information, so the main application of a single bearing is homing towards a target. We simply follow the bearing until it leads us to the source. On the other hand, if we're able to take bearings from multiple locations, these can be plotted together to compute the most probable location of the target, a process often called triangulation. Triangulation, such as the one shown here, is a simple mathematical calculation. The accuracy of the triangulation result is entirely a function of the accuracy of the bearings that are used to produce it. Accurate bearings yield accurate triangulation results. In most cases, 3 or 4 good bearings yield good results. Increasing the number of bearings above more than 5 or 6 doesn't usually yield much additional accuracy. Note that in the real world, bearings will rarely all intersect precisely at the same point, and it's often necessary to discard obvious flyers, or so-called junk bearings, that clearly are not pointing towards the true source of the signal. There are also two methods of obtaining bearings. The first of these involves some type of manual process. This means that the operator manually moves or points the antenna until the strongest signal level is observed. Note the use of the word observed. In most cases, it's a human operator that makes the determination as to when the antenna is pointed in the right direction. This does, of course, mean that manual bearings tend to be somewhat operator-sensitive, which can be either good or bad, depending on the operator's skill level and expertise. This manual methodology is the first methodology we'll discuss. However, serious direction finding is usually based on automatic direction finding methodologies. In this case, our system automatically determines bearings based on one or more changes in the signal characteristics. There are many different types of automatic direction finding, such as Doppler, Watson-Watt, etc., and we'll spend the majority of the remainder of this presentation giving you a technical overview of how they work. One last important topic before we get started is something called multipath. As the name implies, multipath means receiving a signal from multiple directions simultaneously. Radio frequency signals can be reflected from radio-opaque objects, such as concrete, metal, etc., and this means that the signal may appear to be coming from the reflection point, rather than from the source itself. This is a particularly significant issue in urban or mountainous areas. Many of you have had the experience of sitting at a stoplight or stop sign, and having an FM radio station signal get stronger or weaker as you inch the car forwards. The change in the signal strength and the quality are due to the multipath profile at that particular point. In direction finding, having a signal that appears to come from multiple locations, or which changes level due to constructive or destructive interference, is a significant problem, and it's safe to say that multipath is usually the single biggest challenge in direction finding. As we'll see in this presentation, a good direction finding system is usually one that does a good job in dealing with multipath. We mentioned a moment ago that we can divide direction finding methodologies into manual and automatic methods, so let's start with angle of arrival direction finding based on manual techniques. We started our presentation by saying that all direction finding methodologies use a change in amplitude, frequency, or phase to determine the direction towards a signal. Manual determination of angle of arrival is based on amplitude comparison. This is a fancy way of saying that a directional antenna is physically moved or rotated until the maximum received signal strength is obtained, usually via visual inspection by the system operator. The directional antenna can be either handheld, such as the one shown in this picture, or mounted on a tripod or vehicle. Although a directional antenna is required for manual angle of arrival, the type of directional antenna will vary based on the application, such as Yagi, log periodic, or horn antennas. The angular bearing is normally determined and/or recorded using a manual or electronic compass. The biggest advantage of manual angle of arrival is that it's low cost and portable, especially when it's done using handheld antennas and portable receivers. Even with a tripod or other mounting device, these types of manual systems are almost always man-portable and can be quickly deployed in almost any location with minimal setup time. And depending on the type and nature of the target signal, manual angle of arrival based approaches can often yield acceptable results. That said, there are a number of limitations when it comes to this approach. First, since the antenna is usually being manually manipulated and the bearing determination is being manually made by a human operator, the effectiveness of this methodology can be strongly dependent on the operator's skill level and experience. Accuracy can also be poor for distant targets due to the human aspect as well. Even with a tripod and a very narrow antenna pattern, the amount of humanly introduced bearing error can lead to substantial location errors at distances of more than a few hundred meters. Antenna choice is also problematic, since like all other antennas, better directivity of the antenna usually means lower antenna bandwidth and higher side lobes. There's a practical limit to how narrow of an antenna pattern we can use in direction finding. And lastly, manual angle of arrival techniques don't work well when trying to locate short-duration signals. A signal that only appears for a few seconds at a time can be there and gone before the operator has time to rotate the antenna and determine/record the bearing. Now that we've covered manual direction finding, let's move on to our first automatic direction finding methodology, Doppler. The Doppler effect, or Doppler shift, is named after Christian Doppler, who first described it in 1842. As most of you already know, Doppler shift is a type of frequency modulation caused by relative motion. If objects are moving towards each other, relatively speaking, then the frequency of the waves emitted by one object will appear to increase. Similarly, if the objects are moving away from each other, then there is a downward shift in the frequency. Doppler shift applies to many different domains. All of us are familiar with Doppler shift in the audio frequency domain, such as the change in pitch in the whistle of a passing train. Doppler shift also occurs in the visible energy domain, such as the red shift of stars moving away from the Earth. In the radio frequency domain, we can apply the principle of Doppler shift for the purposes of direction finding. Recall that if we move towards a signal source, the received frequency of the signal will shift upwards. If we move away from the signal source, the received frequency will move downwards. If we're able to detect and measure this shift, we could then determine whether we are moving towards or away from the signal source. That is, we could obtain a bearing. So in order to use Doppler shift for direction finding, we need to find a way to move our receiver, or more precisely our antenna, in such a way that we can generate and measure a Doppler shift. There are, however, a couple of problems with this approach. First, since our target may be stationary, we would have to move the receiver to guarantee a Doppler shift is present. And even if this were possible, could we move the receiver fast enough to create a measurable Doppler shift? As we just mentioned, it's not the receiver that needs to move, but rather the antenna. So how do we move an antenna in such a way as to create Doppler shift? Imagine that we have a single antenna mounted on a rotating disc. As this disc is rotated, the antenna will move closer to, and then further away from, the transmitter. At positions A and C, the antenna is stationary relative to the transmitter. That is, the antenna is neither moving towards nor moving away from the transmitter. This means that the Doppler shift is 0 at positions A and C. At position B, we have the maximum speed moving away from the transmitter, and at position D, we have the maximum speed moving towards the transmitter. As we can see from the graph, the Doppler shift creates a so-called Doppler sine wave. This wave reaches a maximum value when the antenna is at position D, and there are 0 crossings at positions C and A. The second 0 crossing at point A represents the position or angle that is closest to the transmitter. By making continuous measurements of Doppler shift as the antenna rotates, we can derive the information needed to determine a bearing towards the target. There is, however, a slight issue with this methodology as we just described it. Namely, an antenna on a rotating disc is not practical. The required rotational speed is much too high to be physically implemented as a vertical antenna on a spinning disc. We can, however, simulate a rotating disc by using an array of antennas, usually 4, and then rapidly switching between them. Each of the antennas is used to generate a series of Doppler pulses, and the system uses these pulses to synthesize the Doppler sine wave. Needless to say, the switching between the antennas must be very fast in order to accurately synthesize the Doppler sine wave using inputs from 4 discrete antennas. Let's look at some examples of Doppler antennas. As we just mentioned, most Doppler DF antennas have 4 elements equally spaced with vertical polarization. Keep in mind, however, that not all DF antennas with 4 equally spaced elements are Doppler antennas. In many cases, Doppler antennas are vehicle-mounted, but Doppler antennas can also be fixed-mounted or configured in a man-portable package. All of the antennas we saw on the previous slide had 4 vertical elements, and this is, by far, the most common configuration for Doppler DF antenna arrays. It's possible to have Doppler DF antenna arrays with much larger numbers of antenna elements, the idea here being that our synthesized Doppler sine wave will be more accurate if we have more measurement points. It is true that larger numbers of antennas improves Doppler DF results, but this only applies if we also increase the diameter of the antenna array. It's also worth noting that some Doppler systems have multiple sets of antennas to cover wider frequency ranges. For example, the array shown in this picture has a total of 8 elements, but it's really just 2 arrays of 4 elements each. The longer antennas cover VHF, and the shorter antennas cover UHF. Doppler DF is a DF methodology often used by hobbyists, for example amateur radio operators, mostly because it's relatively low cost. However, Doppler is also used in both commercial and military direction finding systems, one example of which is the LoJack system used to track stolen vehicles. If you've ever seen a police car with 4 antenna elements on the roof, or maybe even a police helicopter with a similar, but inverted array, these are almost certainly LoJack antennas. After a vehicle is reported stolen, the LoJack network sends out a signal that activates a vehicle locator unit that's installed within the vehicle. This vehicle locator unit, or VLU, sends out a VHF signal that can be tracked by ground and air-based police units with installed LoJack systems. Doppler is a good direction finding methodology to use in this application for several reasons. First, since the make, model, and general appearance of a stolen vehicle is usually known, operating in homing mode with relatively low accuracy is still sufficient for locating vehicles. Secondly, the low cost of the system is important as the number of equipped police vehicles increases. The first of the practical considerations regarding Doppler DF is something we've mentioned several times already. It's relatively low cost compared to other DF methodologies. Part of the reason why Doppler is so low cost is that it's possible to build a Doppler system using simple vertical antennas and an off-the-shelf receiver. Commercial Doppler DF systems usually have a specialized DF receiver for better performance. There are also a few drawbacks that are inherent to Doppler DF. First, Doppler DF systems more or less require that the target signal be a constant CW or similar type signal. Doppler doesn't work well for locating intermittent signals, that is, on and off signals, or very broadband or noise-like signals. The antennas or antenna elements in most Doppler systems also limit the useful frequency range for Doppler DF. Almost all Doppler systems are designed to work at VHF or UHF frequencies, so Doppler isn't a good choice for DFing at either HF or microwave frequencies. And because Doppler antenna arrays are made up of vertical elements, these arrays don't work well when trying to locate horizontally polarized signals. The loss from cross-polarization can easily be 20 to 30 dB. It's fairly safe to say that Doppler is something of an entry-level DF system that works well for certain applications, but suffers from some important limitations in other applications. Doppler can be classified as a frequency-based direction-finding methodology in that it uses changes in frequency to determine the direction or bearing towards the source. The next methodology we'll be looking at is something called Watson-Watt, which is an amplitude-based DF system. More precisely, Watson-Watt is an amplitude comparison system. It's one of the older DF methodologies, having been developed shortly after the First World War. The methodology is named after its creator, Sir Robert Alexander Watson-Watt, who was one of the pioneers in the field of radar. The Watson-Watt direction-finding methodology requires the use of a special type of antenna, either an Adcock antenna or a cross-loop antenna. More on this shortly. Note that Watson-Watt is the name of the methodology used to process information that's obtained from an Adcock antenna. It would be helpful to start by discussing the basics of Adcock antennas. We start with 4 equally spaced vertical elements arranged in pairs. This creates an antenna pattern consisting of 2 figure-8 shaped lobes. For each of the 2 figure-8 shaped patterns, we have maximum sensitivity along the axis and nulls perpendicular to the axis. As we'll see on the next slide, this arrangement yields a unique set of magnitudes for every direction, and an omnidirectional sense antenna is used to resolve any 180-degree ambiguities. Let's walk through a couple of examples. Here's our Adcock antenna again, with the 2 pairs of paired antennas, each creating a figure-8 pattern. For ease of discussion, we're going to refer to 2 axes, the north-south axis for our green antennas, and the east-west axis for our blue antennas. Note that the nulls in these 2 patterns are orthogonal, or at right angles to each other. A signal originating due west, that is with an azimuth of 270 degrees, will have a large measured amplitude on the east-west axis, that is the blue pattern, but very low measured amplitude on the green north-south axis because this angle falls into the null of the green figure-8 pattern. Similarly, a signal arriving from the north, or with an azimuth of 0 degrees, is sensed very strongly on the north-south axis, but almost not at all on the east-west axis. And a signal that arrives from the northeast would, ideally, result in equal measured amplitudes on both antenna pairs. It should be easy to see how we can determine direction using this type of antenna pattern. The 180-degree ambiguity we mentioned on the previous slide refers to the fact that a signal arriving from the west and one arriving from the east will create the same set of magnitudes on the east-west axis, but this is easily dealt with using a simple sense antenna that's usually placed at the center of the array. There are quite a few ways to physically implement Adcock antennas. Most typically, the individual antenna elements are implemented as monopoles when we have a ground plane to work with, or as dipoles when we have a pole-based or tower-mounted application. You can obtain the same type of pattern and behavior using a pair of crossed loops. With regards to the arrangement of the elements, the biggest question is how far apart to space the elements. This spacing is a compromise between accuracy and sensitivity. Placing the elements closer together gives us higher accuracy, but we get better sensitivity when the elements are spaced further apart. Note that in some cases, additional pairs of Adcock antennas can be used to overcome some of these constraints, but this is relatively uncommon in practice. In addition to cross loops, there are a number of different ways to create Adcock antennas, or antennas that yield the desired pair of figure-8 patterns. These include things like crossed ferrite loops, where the loops are wound around conductors, as well as the crossed dipole elements and crossed monopole elements that we mentioned earlier, the latter being more appropriate when we have a ground plane, and the former better suited for pole or tower-mounted applications. And here are a few examples of what these look like in actual implementations: crossed loops, a crossed monopole, and a cross dipole. Note the mounting of the monopole versus the dipole antennas. It's also important to note that one could quite easily confuse some of these antennas with typical Doppler DF antennas based on the number and arrangement of elements. Like all other direction finding methodologies, Watson Watt has its own particular set of advantages, disadvantages, and practical considerations. One of the ways in which Watson Watt distinguishes itself from other direction finding methodologies is that it's well suited to HF direction finding, mostly due to the ease with which we can implement smaller antennas at these frequencies. Compare this to Doppler, which is usually limited to only VHF and UHF. Watson Watt is also very fast. There's very little calculation of results required before we obtain a bearing. We're simply comparing the amplitude on two different antenna pairs. Watson Watt has good accuracy and sensitivity, with the accuracy depending primarily on the circularity of the antenna patterns, something that's not difficult to control. The main drawback to Watson Watt is that it can't measure elevation in addition to azimuth, and if our target is significantly higher or lower than the plane of the antenna, accuracy can suffer. An example of Watson Watt in the real world is the U.S. Coast Guard's Rescue 21 system. This system, which is primarily intended to locate vessels in distress, uses over 225 Watson Watt-based DF sites located along about 40,000 miles of coastline. As you might imagine, being designed for search and rescue, speed and accuracy are critical factors, and the Watson Watt methodology meets both of these requirements very well. Remember also that Watson Watt is well suited to the common frequency ranges that are used in maritime applications, namely HF and VHF. Manual angle of arrival and Watson Watt are both amplitude-based direction finding methods, and Doppler DF is based on changes in the frequency of the received signal. Our next methodology, correlative interferometry, is different from the previous discussed methodologies in that it's based on changes in phase. Like many other direction finding methodologies, correlative interferometry was derived from another application, in this case radio astronomy. Correlative interferometry determines bearings by calculating differences in the received signal's phase, as seen at multiple co-located antenna elements. CI antennas almost always use an odd number of antenna elements arranged in a circular pattern. Let's take a closer look at how this methodology works. For our example, we'll use a 5-element interferometer. We place these 5 elements in a circular pattern, with one of the antennas, here antenna 1, being designated as our reference channel. When a signal arrives at our array at a given angle, say 45 degrees, the measured signal will be phase offset at each of the 5 antenna elements. We then record these offsets for each element and at each angle. This calibration is typically done for each reference angle, 0 to 360 degrees, in increments of 1 degree. The end result is a table that contains phase offsets for all incoming signal angles. Measuring phase differences is where the interferometry part of this methodology's name comes from. Now that we've explained the interferometry part, let's explain the correlative part. When a target signal arrives at our antenna array, we first measure the received phase offsets at each antenna. We then calculate the correlation between our measured phase offsets and the calibrated or ideal phase offsets for each arrival angle 0 to 365 degrees. This process should yield a clear correlation peak, and using this peak we can derive the bearing or arrival angle. One thing that makes correlative interferometry different from other direction finding methodologies is that in addition to delivering a bearing result, we also get a bearing quality. Both of these correlation graphs yield a peak that corresponds to a bearing of 127 degrees. However, the graph on the left shows much stronger correlation at this angle than the graph on the right. So while both sets of results produce the same bearing, we would have a higher degree of confidence in one of the results than in the other one. This type of bearing quality result is unique to correlative interferometry. Antennas designed for use in correlative interferometry usually have an odd number of elements, typically 5 to 9, and these are enclosed within a radome. Depending on the characteristics and placement of the antennas, a CI array can cover a very wide frequency range, up to and above a gigahertz. CI antennas can also be implemented in very small packages with good accuracy, but the array's immunity to things such as reflections and multipath increase as the diameter of the antenna array increases. It is, however, worth noting that compared to the other DF methodologies we've discussed so far, correlative interferometry places fairly strict requirements on the antenna in terms of design and manufacturing. You can easily homebrew antennas for manual DF, Doppler, and Watson-Watt and still get reasonably acceptable results. But CI antennas require very specialized engineering and production resources. So why use correlative interferometry over less technically demanding methodologies such as Doppler or Watson-Watt? Correlative interferometry has several significant advantages. The first is very high accuracy, usually 1 degree or less in an ideal environment. No other direction-finding methodology can produce bearings with this level of accuracy. And as we just discussed, correlative interferometry provides both a bearing as well as a bearing quality, something again that no other DF methodology can provide. Because CI compares phase differences on multiple elements simultaneously, it offers higher immunity to multipath compared to other DF methodologies. And lastly, cross-polarization of signals does not affect the accuracy of CI-based systems. This was one of the main drawbacks of Doppler DF. The last methodology we're going to discuss in this presentation is neither a power of arrival nor an angle of arrival methodology, but rather a time-based methodology, appropriately named time difference of arrival. The basic principle of time difference of arrival is as follows. 3 or more receivers are placed in different locations, and all of these receivers receive a signal. In most cases, the distances between the transmitter and each receiver are different, and so the time at which the signal arrives at each receiver will also be different. We can represent these time differences as curves or hyperbolae, the location of the transmitter being at the intersection of these hyperbolae. In fact, time difference of arrival has sometimes been called hyperbolic direction finding because we determine the location of the transmitter using these hyperbolae. Let's look at how hyperbolae are created. To create a hyperbola, we need 2 receivers, and we need to measure the delta time between receive times at both receivers. If our time delta is 0, then the hyperbola will be a straight line between the 2 receivers, because every point on this line is the same distance from both receivers. On the other hand, the hyperbola will be curved if the difference in time of arrival between the 2 receivers is non-zero. If we have 3 receivers, we'll also have 3 hyperbolae, one between receivers 1 and 2, another between receivers 2 and 3, and a third between receivers 1 and 3. The location of the source is at the intersection of these 3 curves. It is of course possible to have more than 3 stations, but it should be clear that a minimum of 3 stations is needed to obtain an unambiguous position fix. A TDOA-based direction finding system is made up of a network of interconnected sensors and a master station. Received signals of interest are digitized, that is, converted to IQ data, and then transferred to the master station over some type of data link. Note that TDOA requires this data to be very precisely timestamped using a shared clock. In most implementations, this precise shared clock is provided by GPS. The master station then calculates cross-correlations using the data from each station, and the result of this calculation provides the time difference, which is used to draw the hyperbolae. As we mentioned a moment ago, TDOA requires the difference in time of arrival, or delta t, and this is computed using correlation. We start by defining a reference time, and then check for correlation at various time offsets. The results of this correlation will yield a correlogram, whose peak value corresponds to the time offset that produces the strongest correlation. When the signal is wideband, it's usually not difficult to find a clear correlation peak for use in TDOA. However, if we have a narrowband or CW type signal, it becomes much more difficult to find a clear correlation peak in our correlogram, as shown here. This time, there's no clear peak to give us the difference in time of arrival, and hence we'll have a hard time generating an accurate hyperbola. It's important to remember that TDOA-based direction finding systems yield better, that is, more accurate results, when trying to locate wideband signals. All of the previously discussed direction finding methodologies, such as Doppler, Watson-Watt, or correlative interferometry, each require a special type of directional antenna or antenna array. TDOA, on the other hand, is concerned with the time at which a signal arrives, rather than the direction or angle from which it arrived, and thus requires collection and timestamping of all data at multiple points simultaneously. Therefore, TDOA-based direction finding is typically implemented in the form of purpose-built sensors that contain both a receiver and a non-directional antenna. These sensors can be more or less permanently fixed in a location, which is by far the most common case, or can be moved. In either case, the sensors require a network connection for sending the time-stamped IQ data back to the master station. They also require power and GPS for both location and timing. And as we'll discuss in just a moment, good accuracy over larger areas requires a large number of these sensors. So dedicated TDOA sensors tend to be relatively inexpensive, and thus have lower RF performance than receivers used in other DF methodologies. Let's talk a little bit more about location coverage and accuracy in TDOA. In general, TDOA results are accurate to about several hundred meters, this being both a function of the methodology and sensors, as well as the type of signal we're trying to locate, that is, broadband versus narrowband. The best accuracy is obtained when the target is more or less surrounded by sensors, and outside of this area, location accuracy can be poor. For example, if our target has sensors on all sides, accuracy will usually be quite good. On the other hand, if the target is outside of our sensor network, results can be very poor. So in a sense, we need to have some idea of where the target is, or will be, before we start deploying sensors. This isn't a problem if we're trying to cover a given area, but limits the usefulness of TDOA in ad hoc direction finding applications. Let's summarize the practical considerations with regards to TDOA. As we just discussed, location accuracy is usually quite good within the received coverage area, that is, when the target is surrounded by as many sensors as possible. And as we also discussed, accuracy tends to be much better for wideband than narrowband signals, mostly due to the difficulty in getting a strong correlation peak, and thus a time offset, for narrowband signals. Adding additional TDOA sensors to the network offers better accuracy, but at some point there's no additional improvement, and calculation time begins to increase dramatically. At some point is usually in the neighborhood of 6 sensors. TDOA also offers something called proximity gain, which is really just another way of saying that you're more likely to receive a weaker signal if you have lots of sensors in the area. The odds of one of the sensors being physically close to the source is higher. And finally, some TDOA algorithms can detect and process out many of the effects of multipath. One commonly mentioned application of TDOA is the location of mobile or cell phones. In most cases, mobiles are within range of multiple base stations simultaneously. Uplink signals from the mobile are received and processed by each base station, which then send timestamped data to a master station for processing. Note, however, that localization of mobiles increasingly involves cooperative, or at least pseudo-cooperative, techniques. In other words, the mobile's location is determined by querying the mobile's internal GPS or Wi-Fi receivers using a data connection. If you're using an application like Find My iPhone, this isn't based on TDOA direction finding. The final topic in this presentation is something called hybrid methodologies. One definition of a hybrid methodology is actually something that's quite common in many direction finding applications, namely, using an automatic direction finding system to obtain the general location of a target, say within 100 meters or so, and then switching to manual or handheld direction finding to narrow down the location to the meter level. In a sense, this is a hybrid methodology, but normally what's meant by the term hybrid is the combination of two different automatic direction finding methodologies. In particular, the combination of an angle of arrival methodology and a time difference of arrival methodology. As we'll see in the next few slides, hybrid methodologies are probably the most exciting new development in direction finding over the last few decades. Let's first review some of the characteristics of angle of arrival and time difference of arrival. As we mentioned before, bearings can be used in two ways. The first of these is homing, which gives us a direction or bearing towards the target. This is most often used in mobile direction finding, where we follow the bearing to find the target. The other method of using bearings is triangulation, where we take and overlay bearings from multiple locations, either using multiple direction finders or by moving our direction finder from place to place. In time difference of arrival, our receivers or stations are usually fixed, and we derive location information using differences in the time when the target signal appears at each station, this being represented in the form of hyperbolae. Note that in angle of arrival, we could use a single mobile DF station to take bearings from different locations, one after another, and then later combine them. A TDOA-based DF system, on the other hand, requires a minimum of 3 stations operating simultaneously to produce unambiguous results. A hybrid scenario uses 2 or more TDOA sensors and 1 or more angle of arrival stations. Let's look at an example. The 2 TDOA sensors create a hyperbola with a target lying somewhere along this line. Instead of using an additional TDOA station to locate the target, an angle of arrival station generates a bearing, which provides the information that's needed to make an unambiguous position determination. We can gain even more flexibility by integrating TDOA and angle of arrival functionality into a single hybrid station. In this case, we have the maximum possible flexibility, both in terms of geography and signal type. For example, if we're in a relatively low multipath environment and are trying to locate a narrowband source, we simply use angle of arrival. If we have a wideband signal source, or if we're operating in a high multipath environment, we could try using pure time of arrival. The operator could also try to use both methodologies, or choose different sets of stations to use as TDOA or AOA to see if the results are consistent, or which set of stations yields the highest accuracy. We've covered quite a bit of ground in this presentation, so let's have a brief recap of the most commonly used direction finding methodologies. Manual angle of arrival is an amplitude comparison methodology, where we manually move or rotate a directional antenna and obtain bearings by recording the highest level of received signal strength. Doppler direction finding is a frequency comparison methodology, which determines bearings using the amount of Doppler shift in the received signal. Watson-Watt is another amplitude comparison methodology, but instead of using a simple directional antenna like a Yagi or log periodic, it uses a special pair of antennas called an adcock antenna to measure the amplitude of the received signal on 2 different axes simultaneously. Correlative interferometry is one of the newer direction finding methodologies and uses a special circular array of antennas to measure phase differences at each antenna. By testing for correlation between the received and calibrated phase offsets, the system can not only calculate a bearing, but can also provide a measure of that bearing's quality. Time difference of arrival doesn't measure changes in the signal's amplitude, frequency, or phase per se, but rather uses a set of multiple stations to measure differences in the arrival time. These values are used to draw curves, or hyperbolae, which intersect at the transmitter location. And finally, we took a brief look at hybrid methodologies, which leverage the strengths of both angle of arrival and time difference of arrival to provide greater flexibility and accuracy, as well as the potential for integrating both methodologies into a single receiver/antenna unit. This concludes our presentation, An Introduction to Direction Finding. Thanks for watching.